Then after that, what do you have? The signal goes to LC. So LC filter. So, and that is straightforward. Okay, whatever you get the input, it will get filtered out. So, V out by V in, simply V in means VSW actually. So, what will be the, and this filter we have to include everything, RDCR, and then, so I am combining the resistance of the two switches and making into one. So, I will just call it R loss, which has all the resistive losses including your power switch and inductor. VSW is the input, and then at the output you have capacitor. What do you have? Load, R load, and if this is V out, all we need to find the V out over Vs. Sorry. Correct. Okay. What is Y2? SC plus 1 over R load. What is Z1? SL plus R loss plus 1. Solve it. S square LC plus R loss CS plus L over R load S plus R loss over okay. So, I can write this 1 over LC S square plus divided by LC. So, this will become, let us take this common. So, this will become R loss over L plus C, no, okay. And this is your constant term, R loss over R load plus 4. Correct? So let's say if I assume that my voltage is roughly 1 to 1.2 volt, order of like some 1 volt of range, and your R loss, you know, like let's say 50 milliohm your DCR, 50 milliohm your RDS on, roughly 100 milliohm. If I want to drive 1 amp current, what will be R load? Order of amp, order of ohm. So which means your R loss is much less compared to R load. We can make this assumption for simplicity. The reason I am saying, but I mean it will change your resonance frequency. The ratio of R load and R loss will change your resonance frequency, but at the maximum load, if you consider, still R loss is a small portion of your R load. So your resonance frequency will not change that much. So you don't really necessarily need to consider this factor for stability actually, because your resonance frequency will not move that much. So can we get rid of one term here also? If I take R loss over 1 over R load C, R loss, no, anyway leave it, C. Plus 1 over LC. So this is your standard second order low pass filter, correct? So what is the Q? What is the omega naught? Resonance frequency 1 over LC. What is Q? So omega naught over Q naught is this term, R loss over L plus 1 over R load C. Okay. So from here you can find Q naught equal to omega naught over R loss over L plus R load C. So 1 over square root LC divided by R loss C plus okay. So this will become square root LC over R loss C plus so this is your Q naught. So if I want to plot magnitude of HLC, how will it look like? Band pass?
It will look like at O.
What was the transfer function? Band pass or low pass? Second order low pass filter, okay. What is this frequency? Omega naught. And where is the Q? Height of this, okay. What about the phase? How much? Minus 90 at omega naught. But where actually it will go? Try to approach. You have two poles, and very high Q. So it will be very sharp. Okay. So it will almost touch 180 degree because of the high Q. So 0 to minus 180, and this will be minus 90. Okay. So this is your phase of H of LC. So what will be the worst case condition for phase shift in terms of Q? Maximum Q or minimum Q? Maximum Q, So Q naught equal to, so Q naught is max when R load is infinity or no load. So Q naught max equal to square root LC over. So load is variable, but R loss is fixed. So you cannot make any assumption for R loss absolute, but for absolute R load you can always make assumption, because at very light load you can assume there is no load at the output. So 1 over R loss square root L over C. Okay, which means for reduced losses your Q is increased. So there is a trade off between your, in terms of, if you look at a phase shift here, if you are looking at a higher efficiency, you have to reduce the losses, which means you have to choose the inductor with the low ESR, DCR, and MOSFETs with the very low RDS on. So what would happen actually, your Q naught will be max under no load condition, and that's where you assume that it's a worst case when you try to analyze the stability, because at omega naught your phase drop will be larger at higher Q naught. So you guys remember when we were talking about how to choose L and C. So if you I mean, for the same omega naught, it's the product of L and C, if you use a smaller L and larger C, what would happen?
There will be peak to peak ripple current.
No, peak to peak ripple current will be higher, that is fine, but in terms of transient response
Better.
it will be better. Okay. So if you talk about Q naught will reduce. Okay, which means the phase drop at omega naught will be less compared to if you choose a higher L and a smaller C. So you have to be a bit careful. It's not only dependent on R loss, it's also dependent on ratio of L over C. Okay, you can choose a higher value of L and a smaller C for the same efficiency. Actually, you can choose a better inductor, higher value inductor with a smaller DCR, okay, and the capacitor. So as long as your product of L and C remains same and your DCR remains same, So your R loss is not going to change. It doesn't matter what L you choose, but the ratio of L and C will matter, and it will change your Q naught. Okay. So basically nothing. If you remember the second order system when we are talking about, so you had a damping factor, so higher Q means lower damping factor. So your pole will start moving towards j omega axis when a higher Q, and you will get more ringing in the output. So now anything else left? So we have covered all the stages. Now let's try to do the small signal for this. So small signal or small signal model. So this was your V out, output of HLC. Then you had driver stage, so let's call it H DRVS. G of PWM, correct. Then we had an amplifier with gain of A. Then you had what did we have? Beta. Okay. So since our we were feeding the feedback voltage to the negative terminal, so this will become minus A. Okay. So negative feedback. So this is your small signal model. Okay. And all so what will that loop gain transfer function? So if we break the loop here, okay, and you apply, or let me just draw a new figure for this. So this is your closed loop small signal, and let me do this. Minus plus so this was Vref, and you had a beta factor here. Okay, this is complete closed loop. Okay.